Okay, so our last speaker for today and for the whole Midrasha is Frederic Klopp, and he will tell us about the ground state of a system of interacting fermions in a random field, localization, entanglement, and entropy.
Thanks very much. As you may have noticed, I changed my title a little bit. So first, let me thank the organizers for setting up this very nice conference, in which, very informative for me at least, I learned a lot of things. And it was a pleasure also to be back in Israel for actually almost 2 decades. I haven't been here. So well, I'll tell you about some work that has been developed over a number of years with actually former PhD students. Vadim, who is supposed to defend his PhD next week, I think, and Nikolai, who defended a few years ago. And it's going to be, actually, I'm going to come back to the very beginning of the conference, to the first line of the first slide of the first talk by Jonathan, right? And the first line of the first talk by Jonathan contained the following words: transport in a disordered medium, right? And that's actually what my talk is going to be about. And the difference with actually what we saw up to now is that what I'll be considering is not a single particle being transported, but many interacting particles together, right? Which is a subject to which a lot of physics was devoted, but unfortunately not as much mathematics, right? But this has reasons, right? It is difficult. So as the subject is difficult, my goal is going to be modest, right? So let's set up the thing. So on the large cube, I guess this is the pointer, yeah. On the large cube of the space RD, maybe I should take this a little bit further away, as I'm used to speaking loud. That's going to be enough. On the large cube of RD, we consider a random Schrödinger operator. So take any of the models that have appeared up to now. You could even take a random matrix, right, in many dimensions. This will be our single particle model. So our single particle will evolve in this random medium. And we will be dealing with fermions, right? So we're going to consider first n particles, right, evolving without interaction inside this medium. Okay, so we take the antisymmetric tensor product, the n-fold antisymmetric tensor product of a basic space for the particles, and we consider the operator, the Hamiltonian, in which each of the particles is subjected to the same random Hamiltonian. And then we pick a pair interaction potential to keep things as simple as possible, and define an interacting Hamiltonian by just adding our kinetic energy to our kinetic energy, the potential which is made of all the interactions, pairwise interactions, right? The ultimate goal, so you see, two things. We have two variables here. We have the n, the number of particles, and we have the domain, which is a cube, finite cube, over which we study our object. So the goal here is, of course, to let both n and the finite cube grow to infinity, right? And one of the important ways to do that is to keep a fixed density of particles. So in the whole talk, actually, we're going to look at what is called the thermodynamic limit, meaning that the volume of the cube is equal, the number of particles is asymptotic to a fixed constant times the volume of the cube, right? So maybe I can write this down. I didn't put it on the slide. So we're interested in the asymptotics, and approximately rho times the volume of the cube. And so you see that you are dealing with operators in an increasingly larger and larger dimensional space, which is one of the difficulties, right? And what are the questions we're going to address? Well, in the thermodynamic limit, we're going to ask ourselves, what can we say about the ground state energy? So you just take the infimum of the spec. So these are nice Schrödinger operators, right? In many variables, but they're nice Schrödinger operators, right? And as such, we know actually that there is a unique ground state. And what we'd like to say is something about the ground state energy from the physics point of view, it's not the most interesting quantity. It's much more interesting to know something about the associated ground state, right? And in particular, one of the things physicists have been wondering, right? And well, I'm not sure, but maybe I'm not sure, but I think physicists are not, maybe now they agree, but that over some period of time, they didn't completely agree with what's going on, right? What's happening. One of the things physicists have been very much interested in is once you add these interactions, right, and you assume that your random Schrödinger operator is in a localized phase, right? So you assume that the one particle operator has localization. So of course it always has if it's restricted to some cube, but when I mean one has localization, it means that this localization survives when you let the cube go to infinity, right? Meaning that you have nice eigenfunctions that are local, meaning defined essentially around some center of localization, and that when you extend the cube, these survive, right? Of course, the energies are going to change a little bit as you send the cube off to infinity, but essentially the shape of the eigenfunction is going to survive for large enough cubes. Okay, so you're in this localized regime, and physicists are very much interested in what is the fate of such localized states once you add these interactions. Okay? So the idea is to describe, now so the question is to describe the limit. Well, the energy itself, I'm not sure it's of such an interest to physicists. It's to describe more the ground state, right, in the limit, in the thermodynamic limit rho. So you see, as I said, the dimension of space over which you're working, right, is increasing when you let n, when you take the thermodynamic limit. So the one thing, if you want to, it may be difficult to describe the whole ground state. So a typical procedure is to look at what is called the k-particle density matrices, right? Meaning that you integrate out from your state all degrees of freedom except a finite number of them. In this case, you may hope for this thing to have actually a limit, right, when you take the thermodynamic limit. If you take the infinite, if you don't do the integration out and look just at the state itself, then the limit will be some kind of field, which is more difficult to define, right? It's not obvious what space you should look at, what you need to do. Here you're dealing with ordinary operators, right? This is a positive compact operator. It's a trace class operator. And, well, it's because of normalization I took here. So my said here, my states are normalized. So the trace of this is just going to be the number of ways to choose k indistinguishable particles, right, among n. Yeah, and one thing I didn't say, actually, it's in the title, I'm looking at fermions, which means that this is why I take the anti-symmetric tensor product, right? Of course, they are not real electrons because I didn't take the spin into account, right? So, but nevertheless. And so in the non-interacting system, so imagine that you have no interaction, so the u is equal to 0. In this case, things are simple. I'll come back to this later on in the case of the model I'm really studying, but things are simple. What you can do is do the following thing. You define the pre-density of states, right? So you just take the counting function for your finite volume operator and normalize it by the volume. And when you take the thermodynamic limit, right, of this equation, so look at the nth eigenvalue. The nth eigenvalue is exactly the eigenvalue for which this, assume they are simple, right, to make things simple, where this number takes the value n divided by the volume, right? And you see that when you take the thermodynamic limit, if this has a nice limit, which is the case in many random models, right? This normalized counting function has a nice limit, which is called the density, the integrated density of states. Then you can show that actually this energy En has also a nice limit, which is just the limit, so the integrated density of states, it's going to be E rho, which is defined here, which is called the Fermi energy, and it's the solution to the equation n of E rho equals rho, right, naturally. And what is the ground state of this system in the free case? The ground state of this system in the free case is just you take the n first states of your one particle model, right, and sum up their energies. And you take the state which is obtained as a Slater determinant of these n first states, right? And the ground state energy, thus, divided by the volume n, is just going to be the sum of the first n energies of h omega lambda divided by n. And when you take the limit, provided the convergence of the normalized counting function to the density of states is nice, is going to turn out to be just a fixed number, right? Depending just on the density rho. Okay, and so that's a computation you can do in a very general case, right? And which, as there is no interaction, is expressed solely in the spectral data of the full infinite Hamiltonian of one particle, right? Now, for the non-interacting ground state, you can, for example, write down what are the gamma k's. I just wrote down the gamma 1. And the gamma 1, you see, if you integrate, so the psi here is going to be the exterior tensor product of the n first states of h omega lambda, right, of the one particle operator. And if you integrate out n minus 1 variables, the only thing that's going to be left is going to be the orthogonal projector on the n first levels, right, which is nothing but the spectral projector, right, of h omega lambda on the n first levels, which converges to the spectral projector of the full random Hamiltonian when you look at the spectral projector up to energy E rho, the density, the Fermi energy, right? And so you have a nice statement for convergence, and of course, in the same way, you can compute gamma psi k, right, in the free case for any k. So you get a complete picture, right, if there are no interactions. If there are no interactions, you get a complete picture of what happens to the n times symmetric tensor product, or to the n particles in the free case. And well, what is interesting, of course, is once you add the interaction, and there you need to do something, right? So maybe there was one more remark I wanted to make. Yeah, anything else? Come up with something. Okay, so let's go on. So I don't expect to be able to make this for a general random operator, right? So what I mean, a general random Schrödinger operator, okay? And so this is why I'm going to consider a very simple toy model as my one-dimensional, it's going to be one-dimensional, as my single particle Hamiltonian. I'm going to take a very simple toy model, right, that has some special features. So this model actually was at the beginning of the study of these random operators. So this is, we're speaking about the late 50s, early 60s, right? The model was introduced on actually both sides of the Iron Curtain, which, well, existed back then. May come back one day, who knows. It was called, well, on the eastern side, the pieces model, and on the western side, the Luttinger C model, right? And it is done in the following. What you do is you just Poisson point, you take Poisson points on the real line, right? So just throw Poisson points on the real line. And you put Dirichlet boundary condition at every Poisson point. And you form the direct sum, right, of minus Laplacian on the intervals you have obtained by splitting the line with these Poisson points, okay? And you get a random operator. So this is, if you want, the skeleton of a random Schrödinger operator. And one feature, so obviously, looking at this, obviously the spectrum is going to be pure point, right? Because it's just going to be a union of pure point spectra, which are Dirichlet Laplacians on some intervals. It's easy to compute what the spectrum is exactly in terms of the Poisson point. It's easy to get the statistics, right? To get a description, and you have very strong localizations because there's probability 1, all the eigenvalues are localized in one of these intervals. Eigenfunctions, sorry. All the eigenfunctions are localized inside one of these intervals, right? So the main drawback of this model is exactly that, is that the localization is so strong, you have killed all possible tunneling, right, between various regions of space. Okay, that's the main drawback of this model. But it's the strongest localization, and it's very simple to describe. And you can compute the integrated density of states explicitly, right? It's a finite formula, integrated density of states. And what we're going to do is we're going to take our n-particle system exactly based on this random one-particle random Hamiltonian, right? But we're going to add to it some interaction. So whereas in the one-dimensional model, right, for the single particle, there is no tunneling possible, because of the interaction, you are still possible to interact at a distance, right? Particles that are far away from one another can still interact depending on what you ask for the interactions. So here I put the strongest assumptions. I take my interactions, well, I want them to be even, right? All the particles play the same role. Of course, not identically vanishing. Bounded and compactly supported. So maybe the most important assumption is the fact that it's compactly supported. So the interaction is still going to be finite distance. But actually, a number of the things I talk about, I try to underline this, don't need the compactly supported part. They assume they are still work if you have some decay at infinity, right? And it doesn't even need to be so fast. It needs to be, well, it needs to be faster than Coulomb, right? It needs to be at least 1 over x to the 4, I think. Well, if you go decay faster than 1 under x to the 4, then a number of the results, not all of them, but a number of the results are still going to be the same. Okay? So, because of the very special Hamiltonian I took here, right, or this is a consequence of the suppression of tunneling, is that you can decompose the Hilbert space, right, in the following way, obviously, right? So the pieces pi j's, if every time you see a capital pi sub j, it means that this is a piece, right? It's one of the intervals where the random Hamiltonian, or where you have, to which you have restricted your random Hamiltonian, right? Well, this, you have this direct orthogonal sum. Of course, the number of terms in the sum is random, right? It's the number of Poisson points inside my interval. Well, I'm sorry, there is some discrepancy. There is, here I put 0L, here I've put minus L over 2, L over 2, right? Doesn't really matter, right? It's the Poisson points that take care of that. Okay, so there is some discrepancy here. I should have put 0L everywhere. So you do this, and of course then the exterior, the nth exterior tensor product of the L2s can be decomposed as an orthogonal. Here the orthogonal is missing, direct sum of spaces where the spaces are just the spaces where you fix the number of particles inside each piece. So you pick a collection, right, of integers such that the sum of this, the sum over the collection of integers is equal to n. You have n particles. And so this is what we call an occupation number. And you fix the occupation number in the pieces, right? And the spectral, the important thing, right, is that you can take this Hilbert space decomposition. So of course these are orthogonal, 2 by 2 orthogonal closed subspaces of our initial Hilbert space. And the Hamiltonian commutes with this decomposition, right? If you look at the Hamiltonian, obviously, the decomposition for the potential doesn't make any difference because it's going to be just multiplying by the characteristic function of some intervals, right? And for the Hamiltonian, because of its special structure, it commutes with this decomposition. What does it mean? It means that if you want to find the ground state, you just need to find the ground state inside some HQ and compare them. Inside every HQ, you can look at what the ground state looks like, right? And you can compare them to see who's the ground state of the whole system. Okay, and this makes things easier because you're dealing with, you know where the particles, your n particles, are living. Okay? So, and this way you can, for example, analyze the non-interacting ground states, so fix an occupation. Then if you look at the ground states for this occupation, so you look at the infimum of your operator on HQ, well, this is just the sum of the ground states in each of the pieces, right? This can be computed explicitly. And in particular, what you see is to find the total ground state is minimize this functional under the constraint that the sum of the QJs is equal to n. That's the way to find it, right? And one important fact is that the function that to a number, so fix a piece P, take the function that to a number of particles inside this piece associates the ground state of this operator. You put Q particles in a single interval of length L, right? Submitted to just the free Dirichlet Laplacian. This function is convex, which means that if you look at if you look at the number, the ground state energy when you take Q plus 1 particle minus the ground state energy when you take Q particle, this is an increasing function, right? This is an immediate computation, right? That's an immediate computation. You can compute all these numbers explicitly. I didn't write them out because it's not necessary. So this is what enables you to construct the ground state for the free thing, right? What you do is you pick order, so you define the Fermi energy and the Fermi length as being the shortest interval that has some energy less than or equal to the Fermi energy, right? And then for each of piece, you take all the states associated to all the levels below this Fermi energy, right? And you form the Slater determinant of this. So this tells you that if you look at the ground state, in pieces that have a size L rho to 2 L rho, you have put 1 state. In pieces that have size 2 L rho to 3 L rho, you put 2 states, and so on, right? In larger and larger pieces, you put more and more states, right? This is what you get through the optimization through this thing. And now what happens when you take the interacting ground state, right? At the interaction. Well, the basic lemma, the important thing you have to notice is the following. There exists some constant such that if you take small rho, when L is large in the thermodynamic limit, with a very large probability, if you define the length L rho of U to be this, to exact value is not important, but it's going to be, you see L rho is of size 1 over log rho, it's got size log rho, and this is much smaller, rho is small. So this is of size log rho, modulus log rho, sorry, and this is of size rho, so it's much more than that, right? So this is roughly of the same size as the Fermi length. If you take any ground state, if a piece is of length, so that's the length of my piece pi I, less than k times L rho, then for every occupation for this ground state, meaning that when you project on Q of psi and you get something which is not vanishing, well, the occupation at psi j is at most k minus 1. Even for the interacting ground state. Even though you put it, what does it mean? It means that if you take pieces and look at pieces that are of length less than this, then they contain no particle in the interacting ground state. Right? Apply this for k equals 1. If the piece is has a length less than L rho U, then we know that it is empty. Pieces that contain at most that have length at most twice this, right? So it's a little bit smaller than the Fermi length. You have exactly the same statement in the free case when you remove this small correction, right? But if you take pieces that are slightly shorter, you get the same kind of description as in the as in the free state, right? Well, you get another bound which is similar in the sense that you know that it contains at most that many particles, right? And so this PQ is just the orthogonal projection onto the space HQ, right? Meaning this is a space of fixed occupation. And where does this come from? This comes from the fact, it comes from two things. It comes from the fact that the number of available pieces of a given length, because of the statistics of the Poisson process, right, decays exponentially with this length. If you look at the intervals, right, the piece's length, because the process of the xk was Poisson, these are essentially IID exponentially distributed random variables, right? Oh, the Poisson, I didn't say that, take it to be intensity 1, right? The initial Poisson I just fixed to be intensity 1. So this intensity is fixed. And so, shorter pieces are much more likely. There are many, it means that there are many of them. And I know that rho is small. There are actually few particles. What does it mean? It means that every time you break this, you can take the top particle in here and move it to some other piece, which is of length larger than that, so very close to the Fermi energy, right? Which is not interacting with any of the pieces that you have populated yet, because there are few of them, right? And which enables you to diminish the total energy of your system, right? This is what you can do. And so, what does this mean? this means that now actually our system looks very much like the free one if you change some definitions, right? Because now fixed in omega, so the length, the pieces' length are fixed, right? And consider all the pieces, so you fix all the Poisson points, right? You choose a sample of your random thing. And then all the length of the pieces are fixed, and consider all of them that are larger than L rho u. And you order them from left to right. So you take the xk, right? And you order these pieces from left to right. Okay? And you group all consecutive pieces. Maybe the picture is in order now, right? So here you have the interval minus of 0L. So you take pieces, and then there are shorter ones, and then there's long one, and then there are shorter ones, long one. So imagine that this is, well, actually, let's take a little bit shorter. This is my L rho u. L rho u. So this one is longer than L rho u, right? Okay. This one is longer than L rho u. So a chain is going to be such a thing. This distance now, so this is much shorter than L rho u, and this distance, let's assume that this is less than du. Right? So du is just the diameter of the convex hull of the support of my interaction. Okay? And now this is another piece. But this is now, let's say, larger than du. Okay? And this is larger than L rho u. Okay? And so you'll have one chain that will be this. Okay? This is one chain. So here we have particles can populate this. Let me put some number. Q J1, J2. But here there's nothing, because these pieces have length less than L rho u, right? And then here you can again populate things, J3, and so on, right? And so consider such chains. So of course these chains only depend on the Poisson points, right? They just depend on the background, random background, background, the potential. And for such a chain, right, that satisfies exactly this. So it's a set of pieces such that the set of functions here is increasing. The length of every of these pieces that has been distinguished is larger than L rho u. The distance between two distinguished pieces is less than du, so meaning that they interact. And the distance of the union of those to a piece that is of length larger than L rho u, which does not belong to this union, is actually larger than this is not capital, this is du, small du, right? And for such a chain, and for an occupation attached to the distinguished pieces of this chain, we can define the following Hamiltonian. In each of the distinguished pieces, we put the Hamiltonian with exactly corresponds to qj particles interacting, and then you have the interaction between neighboring pieces, right? Take these Hamiltonians. Then, if you look at the ground state, a ground state, yeah, in this model, actually, it's not obvious that the ground state is going to be unique, right? This comes from the fact that we're not dealing with a Schrödinger operator, right? In the sense that I put the pieces, it's a sum of Dirichlet operators, right? But the ground states could actually be multiple because of that.
For fermions, it's always true that it can't be, might not be.
No, if you speak of Schrödinger operators, but this is not a Schrödinger operator, this is a sum of Schrödinger operators.
But even for single Schrödinger operator fermions, it's not.
Yeah, but this is a sum. This is exactly the problem, is that because it's a sum of Schrödinger operators, two of the Schrödinger operators could have the same ground state. You see, of the HQ, for a given HQ, it's a Schrödinger operator. I agree with you. If you look at HQ, then the ground state is unique.
No, even for fermions, it's
Oh,
not unique even for a single Schrödinger operator.
Except in dimension 1. Because there is no multiplicity, right? These come from the thing in dimension 1. What you're talking about is, I agree with you that you may have multiple states.
Eigenvalues are given by sums.
Yes, I agree with you.
Sums might happen to be equal.
Well, in the free case, no. In the free case they can be. Actually, the reason you are making it is not enough. Actually, it's because it's one-dimensional. It's not going to happen.
Yeah,
Okay.
sorry.
No worries. So to take a ground state and assume that you have some what I call it distribution of some occupation exactly some occupation such that the projection of psi on this occupation is non-vanishing, right? So this is an occupation appearing in psi. So psi in general is going to be a sum of different psi q's. Then you can rewrite the psi q as the exterior product of a chains, and each of the psi chains here, right, is going to be subjected to such Hamiltonian. And so you get that the energy of this psi q is going to be the sum of these energies over chains. And so now if you want to find the ground state, you just have to minimize this sum of the energies over chains under the constraint that the total number of particles is equal to n. So it's exactly the same thing as in the free case, except that you changed, right, the local Hamiltonians. They are now the Hamiltonians over chains. Okay? And then to solve this, right, one of the difficulties is, the question now, if you want to use the same method, is that you will need the convexity of the energy, the ground state energy of a single chain in terms of the number of particles inside the chain. And unfortunately, the local convexity of the local energies is a difficult question that I don't know how to solve in general. Right? So that's one of the big open questions for this model, is to prove that the mapping that to the total number, actually here the Q should not be Q, it should be modulus of Q, meaning the total, it's the total number of particles inside the chain. This should be convex, right? If you know how to do that, then you'll be happy, and you can apply the same method and find the ground state in exactly the same way as the free case, right? If this is not convex, you can't apply the same method, right? Because when you order the energy levels, right? I mean, you can define the energy levels, but the energy levels are not going to be ordered in the same way as they're numbering locally, right? If this function is not convex, it means that, you see, what is the energy levels? An energy level for this thing would be every time I increase the QC here, right? Every time I increase the QC, yeah, this should be QC actually, I should have put the QC here. Every time I increase the QC, the ground state, if I take the ground state energy of HC, QC plus 1, subtract the ground state energy of HC, QC, I should get something which is increasing in QC. Because these are the natural levels that you distinguish in this interacting system. If these are not increasing, what may happen that if you define the levels as being the difference of the successive ground states, it may happen that there is a shorter level which is coming up further, right, for a larger number of particles. And you cannot just order them, the levels, right, and choose among them, because they come up for a larger QC, right? So it's the same difference as trying to minimize a functional which is not convex, right, from a functional which is convex, right? Because convexity then gives you that you can minimize roughly locally every one of them here. The fact that it's not, so if this is not convex, you can't just minimize locally each of these terms. So unfortunately, as we only know the convexity for very short chains. Essentially, we only know that it's convex if I take chains that have one component or two components. Already at 3, there are possibilities of non-convexity that I can't rule out. I don't know how to do it. So that's a good open question. And for example, so one thing I wanted to state now is what happens if you take, so this is just for the definition of this gamma star, right? So I put in. And the description of the interacting ground state now. So yeah, one thing I want to say here is what this enables you to do is, well, now there are two things. Again, because of the exponential decay, right, of the number of pieces having a length larger than L, right, this decays exponentially in L, we know that long pieces are much rarer than short pieces. We also know that they cannot contain too many particles. So most of our particles are going to live in the shortest possible pieces, right? So roughly you are going to have somewhere about almost rho particles living in pieces that are of size almost L rho. Then you have rho square particles that live in pieces that are of size almost rho squared. Right? This is still going to be true. And what does it mean? It means that if we know the convexity for short chains, we are going to be able to apply this optimization procedure, right? Except for a number of particles, which is of order, right? Essentially, the chains that we know have to control is length 2 plus delta times n. So we can't, 1 plus delta times n. So we can control, so we have n particles at n, and we can control all particles but that number. If you know it for longer and longer chains, right, you would be able to improve this exponent. If you can take chains that are of length k, right, they contain k of those, then you are able to improve this to essentially k minus 1 plus delta. Okay? And so in this way, what you can do is you can get, so let me just, this is just to show you the following figure. So how, actually, is there a clock somewhere?
Behind the board.
Oh, behind the board, thanks very much. Yeah, okay, that's fine. So what you can do using this is you can look at, so do you remember we had the picture in blue already on the board? This is the distribution of particles for, in blue it's for the free case, and in green it is the distribution for the interacting case. So what you see here is that you've taken some of the blue particles here that were living in intervals or in pieces of lengths larger than 2 arrow, and you've removed one particle here and you've put it to another place, right, where they live alone, but in pieces of length less than arrow, which are forbidden, right, for the free case. So, and in this way you gain energy, right? And you can give a more complicated picture if you add in the case of 2 intervals, right? Which gives you, and this yields expansions for the ground state. Okay, let's come to the ground state, expansion for the ground state energy. Let's come to the ground state. So let's look at the 2 particle density matrices. So as I said, this is, for example, it's just a normalized vector in our exterior tensor product, right? And you integrate all variables except 2. So you get the trace class operator and the kernel, right? Which I write the kernel. So here I doubled the variables. So this is just a kernel for the free ground state. And if you compute it for the free ground state, what you get, right, is that it's expressed in terms of the spectral projector of our random Hamiltonian, right? So here I shouldn't put, here I should put En actually. It's not E rho, it's En, which is the nth variable. Right? It's not exactly the same, right? At a fixed, En converges to E rho, right? But for fixed L and omega, it's going to be En, right? So you can't do anything about that. And what you see, it has a special structure because it's supposed to be anti-symmetric in xy and x prime, y prime, okay? And you see the structure, we know this is the standard estimates of localization in the free case. We know that this is exponentially decaying, right? In this case, it's actually much more. It's exponentially decaying when x and y are apart from one another, or x prime, y prime are apart from one another. And here, same thing. Of course, the other one you can't do without the other one because you are requiring that you have anti-symmetry, right? So this, it's not in, this requires to put the other part. And what you see is that when U is non-vanishing, then if you look now, well, I don't get a pointwise bound on this. I just look at the expectation, right? For rho small enough, you get that the exponential decay of this function is of the same type, right? So you get the same kind of exponential decay. And in physics, right, this decay for the 2-particle reduced density matrix is considered a signature of localization for my n particles, right? So yeah, one thing oh, sorry, it's too low actually.
Sign error?
A sign, oh, sorry, yeah, there's a minus missing here. You're right, actually. There is a minus here. There is a minus here.
And in the second.
And in the second term as well, definitely. Sure, there are 2 minuses missing, that's correct. What did I want to say?
Sorry.
Yeah, no worries. Yeah, what I wanted to say is, you see, yeah, one of the problems I didn't speak of is localization for many particles is not the same thing as for one particle because of the following thing. You have n particles, right? So n is rho, you have rho times the volume particles inside your body, right? Inside a single volume of size rho. And so, of course, the particles cannot be too far away from one another, right? You cannot expect the thing to decay in the usual sense, right? That you have off-diagonal decay of the kernels in all directions. This you cannot expect because the particles live somewhere and they are actually not that far away, right? There are too many of them for them to be far away. So the typical distance between two particles is going to be at most 1 over rho, which is a fixed number. It doesn't increase when n goes to infinity, right? So you cannot expect anything like the usual decay, right? But what you can expect is that you have the same kind of decay as in the free case. And the other thing you can do is you can also look at the same model at positive temperatures. So you look at the Fock space, right? So I take the grand canonical formalism. I looked at the Fock space, I take the direct sum, so these are non-interacting among themselves, right? Each of the operator has interactions, but they don't interact in the Fock space. So you take the direct sum for large over all n, for L fixed. And what you can show is that, well, if you look at this, so n is the number operator on the Fock space, right? So to each sector, it gives the number of particles inside the sector. And you can look at the exponential of h omega L u minus mu times n, right? And you can show that this exponential is actually trace class. And you can define the Gibbs states at temperature 1 over beta, so for beta positive, yeah, right, as being just the direct sum for the Gibbs states in each of the sectors, right? And what you can prove is that, and you can define its 2-particle density matrix. The usual way, you take sector-wise the 2-particle density matrix for each of the Gibbs states. And what you can prove is this, is that, well, if you fix a chemical potential mu that is small enough, then you can find a non-decreasing function, positive value, depends on temperature, for any positive temperature, such that when you look at, so here instead of taking soup norms, right, so there is a soup in L over there, right, I forgot about, there is a soup in L in front of the expectation. If you take, now I don't look at the soup norm, I just take an integral, right, just take something which corresponds to the trace class, right, for this over, for x1, x1, y1, x2, y2, close to xy, x prime, y prime, right? Then this, to regularize things somewhat, not to have to worry about things having too little regularity in the variables xy, x prime, y prime. So taking this integral, you get that you have exponential decay. Here the minus signs are not missing. You have an exponential decay of the same type as before, right? The one you expect, right? In x minus x prime and y minus y prime. Right? So at any temperature, the model exhibits the same kind of exponential decay, so the same kind of localized phase. And well, the last thing is the entanglement entropy. Right, so let me explain what this is. So that's another criterion, right, that was set up by physicists to try to understand if a system is localized, right? So roughly the idea is the following. Maybe I do a picture and draw some picture. Yeah, okay, I have 5 minutes, that should be enough. So take a system, right, and cut it in two, A, B, okay, and well, maybe I do it. So imagine that the line here extends to infinity, and you let the system grow, right? This grows when L grows, okay, and essentially what you do is you take your ground state, right, or at positive temperature or at 0 temperature, and you integrate out all degrees of freedom. So actually, I think in physics they do integrate all degrees of freedom inside 1/2, right? And you'd like to understand, well, essentially the entropy of the state that is here, right? And this entropy, right, is supposed to be depending only, right, asymptotically on the boundary, right, in the case you're localized, and it's going to be of size of volume of B, right, in this case when things are delocalized. Okay? So, in the Fock space you have to do it somewhat differently. In the Fock space you have to do it somewhat differently because if you just split 0L like this, right, in the Fock space when you write the sum, you're going to get something with having variable numbers of particles, right, which you want to avoid. So the way you do it is you use the following proposition. You take this bipartite decomposition, and then you can, if you find an isomorphism between the Fock space over the whole length and the standard tensor product of the Fock spaces over 0, L star, and L star L, using the following formula. Right? That's the way to construct properly the bipartite decomposition, okay, in the case of Fock spaces. And so the reduced density of states is just the following. So take a bipartite decomposition. So here I did it just from the spaces I'm interested in. I consider now a bipartite decomposition in closed Hilbert spaces in general Hilbert. Take a pure density, so a positive normalized trace class operator on the Fock space. Then the reduced density corresponding to this one is just the unique bound operator that satisfies this, right? What is this? This you should see the traces replace traces by integrals. Forget about the i's, the iotas here that are in there that are just this identification. And you integrate against all variables where you have a 1 here. These are the free variables. That's the observable that's free, right? Here you see the free variables. Okay, and you integrate out all the variables in K2, okay, by taking the trace here in K2. And what this gives you is a new operator acting on just the variables that you haven't integrated out, right? And this eta 1 is what is called the reduced density. So if you play with this with the states I have before, you see that the K, what you get is, it's the same definition as before, except that what you take as a partition is just you partition RD as RL tensor RL minus D. D minus L, sorry. And you just take for the entanglement entropy with respect to the space K1, so 0 L star. Why is this? Yeah, why did I denote this by S? That's interesting. Okay, I thought it would have been, yeah, okay. So S of K sub K1 eta is just the von Neumann entropy of this state. So you take the trace of eta 1 log eta 1 and take the opposite. So these are trace class operators, eta 1. Trace is equal to 1. So this is going to be, minus put it inside, so this is going to be a non-negative number. But what is not completely obvious is that actually the state is traceable, right? That's something which a priori is not completely obvious in general. I don't have a result about that. And now if you consider our ground state, right, what we do is we just took the state is where we put 0 in all the other sectors of the Fock space. And we take eta u to be this. The rank 1, this is a pure density, obviously, right? And you can take the reduced density over H star, so this is meaning be over 0 L star, right? And it's entanglement entropy. And what we compute is, in the third order dynamic limit, you can compute the expectation. Actually, you can compute the distribution of this random number. This is a random number, which has a certain distribution. We can compute the distribution up to errors of that size. Right, the thing is the errors, right? And here I just wrote what you get for the expectation, right? And there is a pretty horrible formula for this function, L, right? Which is essentially explicit and which enables you to compare it with the free case and to see actually that this entropy behaves in one dimension. So living on the boundary means that it should be of order constant, right? And you can compute the constant and compute how much it changes when you set u, right? You go from u equals 0 to u different from 0, right? And of course, okay, I think this is it, right? Okay, thanks very much for your attention. Oh no, sorry. There was more to it. I have one, just a short remark. I have 2 minutes. There was more to it, actually. This was everything about the simple model. Yeah, okay, no. Well, okay, let's stop it. Let's stop it here. Let's stop it. Yeah. Thanks very much. No, the next slides were about, I can only do this, I'd like to do this for Schrödinger operators, true Schrödinger operators, right? Not the toy model. But the only thing I know how to do is, unfortunately, not the description, for example, of the exponential decay of the gamma 2s, which would be something really worthwhile, right? It's just a description of the ground state if you take minus Laplacian plus v omega, true random operator, right? Then you can do at the bottom of the spectrum for rho small density, which places you at the bottom of the spectrum. Then you can give a description of the ground state, but which is not enough, to my knowledge at least, to be able to be conclusive about the decay of the two-particle density for this ground state, right? So, okay, well.
Questions? I have a little question.
Sure.
So, what happens in the pieces model if you change the pieces model to just another delta type?
Well, if you change to exactly, you can put a delta type, right?
Right.
And everything crumbles because, yeah, it crumbles. I mean, not everything except what I had in the last 3 slides, which is actually very little. It crumbles because you reinstate, right, tunneling.
Right.
I don't know how to control. I mean, there is no such thing as the number of particles defined locally. Right? And all of this analysis relies on this, right? It relies on the existence of this number of particles, right? And I don't know how to do anything approximate.
Okay. So even Neumann you cannot have it.
On Neumann you can. If you take Neumann boundary conditions and cut with Neumann, it's going to give you the same picture.
Okay. So
It doesn't change anything. This doesn't change anything.
Okay.
No. You can try to approximate from above and below Neumann, but this is not going to give you a good description of the eigenfunctions, right? It's going to be fine to understand something what's happening. So in this way, you can find indeed an estimate on an expansion for the ground state energy, right, per particle, for example. This you can do, but it won't tell you anything about what's happening to the ground state eigenfunction, actually, or to the ground state itself. Right. So. Yes, please.
Suppose one considers a simpler concept of this problem, just finite number of particles, not density, just 2 particles, 3 particles.
There are results. Actually, if you take 2 or 3 particles, right, there are results by a number of people, among which Eisenman, Varsel, Chelyevsky, that prove localization. Because in this finite dimensional setting, right, you can set up localization as, if you take a finite number of particles, you can set up localization estimates in the usual way.
But can you say something about, say, how localization length changes, depends on...
I don't think there are, I mean, you see, one of the problems is that to have an estimate about really what localization length is, right, you need lower bounds on eigenfunctions. And except in 1D, I don't think there is, even for a finite number, even for a single particle, I don't think there are any reasonable estimates on lower bounds on eigenfunctions.
Okay, let it be 1D.
Yeah, in 1D, then you can certainly, well, no, actually, because as soon as you take 2 or 3 particles, you are going to higher dimension, right? And I don't think they get anything more, right, than the usual estimates. You see, the difficulty when you take a small number of particles, right, a few particles, is that you get, again, a random Schrödinger operator, but with less randomness. You get, because every particle is subjected to the same randomness. So you get less degrees of freedom in your randomness, right? And but you have a particular structure of your potential. The potential has a very particular geometric structure. So, and you need to use this structure because you have less randomness, right? But in 3 dimensions, it doesn't relieve you from the problem of understanding local lower bounds on eigenfunctions, which are very difficult to obtain, right? If you look at lower bounds on eigenfunctions, even, I mean, There are some famous problems in harmonic analysis, right, to understand that at large distance, right, an eigenfunction of a second order linear PDE does not decay faster than e to the minus, I think up to now it's x to the minus, what is it, 4. Yeah, I think people know how to show that it doesn't decay faster than e to the minus modulus of x to the minus 4/3, x to the 4/3, right? Whereas what is expected is e to the minus modulus of x, right? It's a famous conjecture about general PDEs. But in general, in higher dimensions, there are no estimates on the. So if you want to talk about localization length, right, get estimates, then you need to understand how they decay, right? The upper bound will not be enough, and what people have is upper bounds.
More questions, comments? Well, if not, let's thank Frederic again.
Well, and being the final speaker, I have the privilege to thank the organizers, Jonathan in particular, but also Anat, right, and all the participants who came to this conference. That was, for me at least, very fruitful. I learned a lot of things, and well, thanks very much.
Yeah, so let me first indeed thank all the speakers, especially for following our request to have at least an introductory component in your lectures. I think for me it was definitely very beneficial, so thank you all the speakers, and I want to thank all the participants for joining us. Okay, you can, I don't know. Thank you. I also want to ask you, you've all probably received already a request from Anat to fill out some feedback form. That's actually very important for the school here, and actually would be beneficial for me as well. So please fill out this form. Just take a few minutes of your time to do this. And finally, I wanted to present Anat with a little flower and to thank her in front of all of you. And I asked her to join us, and she said she was terribly embarrassed and she really didn't want to do this. So I gave her the flower, separately, and I just want to thank her. And if you feel you benefited in some way, then also just thank her personally, because she's just embarrassed to be in front of everybody. And I want to thank the whole staff at the Institute, also Shai, for all the talks went technically very well. Not only technically, but Shai for this, and Inbal for helping. So okay, so thank you all, and I hope to see you here soon again, and if not here, somewhere else.
And lunch is on the ground floor.
And lunch is on the ground floor, right? The most important thing, right?